It's up there, it's 1.045.
No, nothing magnitude, this is omega, right?
Yeah, I got
Right.
the answer.
For omega?
Oh, good.
Confirmation.
Someone else can just put it in the equation to see if it works out. So what does this angle come out to be? So G of J 1.045 is equal to 1.
It
What is the
comes,
angle?
it is negative 114.2.
So does that kind of make sense? Here is 1, here is 3, we got a pole here at 3. We seem to cross over at, let's see, at minus 20 dB per decade, so really close here. And the actual line is going to run a little under, so to think that we cross here at 1.045 totally makes sense to me. 1.045. If we look at this, the angle here is 90, but remember this is swinging down quite a bit here already. It's going to look more like that. So to say that this angle is a negative 114 degrees, does that seem reasonable? So we're pretty happy with these numbers. So what is the current phase margin? 180.
65.8.
So the difference between this and 180, so is 65.8 degrees. Okay, that's what all of that was about. Also, we need this number for something else. We need that number for something else. We're going to take that number and we're going to make a period out of it. So F is equal to 2 pi is omega over 2 pi. T is equal to 1 over F, which is equal to 2 pi over omega. So tell me what the period of this waveform is at omega equal 1.045. It's going to be several seconds long, I think. Because that's 6 something?
6.013.
Seconds. Now the question is, this delay of half a second, about how much of this is it? Isn't it like 1/12 of this time?
Yeah.
So it's about 1/12 of 360 degrees. What are we expecting to decrease our phase margin by? Roughly 30 degrees. Let's see what it turns out to be. So we want to translate this 0.5 seconds into an angle. So what we do is we take 0.5 seconds divided by the period we just figured out. So now we have the fraction of a complete waveform that 0.5 seconds represents. And then we multiply that by 360 degrees to turn it into degrees so we can modify our phase margin. What do you end up with when you do this?
29.9.
About 30 degrees. 29.9 degrees. So what do? Do we make this phase margin bigger or smaller by 29.9 degrees? Yes, because phase causes extra negative angle, negative, it's delay, right? So we say our real phase margin then, our modified phase margin because of the delay, PM becomes equal to 65.8 degrees minus 29.9 degrees equals 34.9 degrees.
35.9.
35.9?
Yeah, it's direct 30 plus 0.1.
Yeah. Let's see what I did. 35.9 degrees. Like the 0.9 matters. I mean, we are way too close. So how do I now translate that into overshoot? Okay. There is a relationship between the two for a very, very simple transfer function, much simpler than this one is, but that's the best we have. And what we have to do first is translate that phase margin into a zeta. And the zeta is approximately equal to the phase margin divided by 100 in degrees. So we go about 35.9 degrees divided by 100 that is a weird, weird relationship. Let me see if I can find it in here. Do you mind if I don't? Okay. It's a response techniques.
This
step right there.
No, that one I got.
Okay.
It's saying everything else.
Systems with time delay, so we still need to get that relationship between, there it is right there. Okay. There is a graph here on page 648. I'll gather you all around here for a second if you would. Will you come here for a minute?
Yeah.
This same development, almost exactly the same development, is also in the Bodson book. And what he has is on the previous page, he has damping ratio from phase margin. So what he's trying to get is zeta from the phase margin. And what he's assuming is that G of S is this, so that the closed loop transfer function becomes this. It has exactly 2 poles at known locations. So he has manufactured a open loop transfer function which would produce only 2 poles in the closed loop. In this. And he says, okay, if I look at these phase margins and I plot the relative zeta, which is that number right there, or I'll change zeta and plot my phase margins, then I end up with this plot right here. So the damping ratio, that's zeta. You may want to write that down in your book. Here's the phase margin right here. So we could look at this and say, for a given phase margin of 30, what was it, 35, we should get a damping ratio of something like this for this very specific transfer function. But we're using it for slightly different. And so essentially what that is the second order approximation.
And that's the question we're being asked, right?
Yeah. So this system results, this is a second order closed loop system.
Mm-hmm.
All other systems that aren't second order closed loop, this number is pretty suspect.
Use a computer.
Now, if you look at this line, you'll find out that these numbers for 10, zeta is about 0.2, yeah, where do you go? Yeah, thank you. See how 20 comes out with about 0.2? 30 comes about, 40 comes out with about 0.4. 60 comes out with about 0.6, a little bit off now, it's starting to lose it. But up to around 60, 65 degrees, this line goes at about a slope of 100. That's where the 100 comes from.
Okay.
Above that, about 60, 65 degrees, it doesn't work anymore. So,
Okay.
okay, so all of that work now.
Sorry.
We got to this. Now, if you look at the example that I handed out to you, the relationship between zeta and overshoot is given. It is also given in your root locus design crib sheet, if you find that. It's a relationship from Bodson's, or from what's his name's book. I don't remember exactly what it is. It's like 2 pi zeta over 1 plus zeta squared, or the square root of that, and then e raised to that power times 100%. I'm pretty sure I've got a mistake or two in there.
Zeta pi. Well, it's close.
So, but something along that line. Let me look at my example
It's
sheet.
right here.
It's written there on the example sheet because you need to have it. He refers to an equation number in here. I'm just putting the equation there. Okay, that is that equation. So, we're about, we got. So that has to be a minus zeta pi on top, 1 minus zeta squared. So I had some elements of it more or less right. I don't remember that equation. Don't memorize it. But that will give you a percent overshoot. Okay. So you go through all of that, and you've got now some of the numbers, so that makes life a lot easier. You then can predict a percent overshoot. Now I believe in BD5, I ask you to do another step here. No, I do that in problem 3. I do that in problem 3. So later on in problem 3, I asked you to use SISO and actually figure out from the real life world, more or less, at least a good simulation, what the overshoot really is. And I find these overshoots to be considerably larger when I figure them out with MATLAB or something else. I used MathCAD myself. So there is no such section here in problem 1 that rounds up problem 1. Rounds up problem 1. Number 2 is easy.